We just found out the displacements at node Q2 and Q4 and Q6. That is at node 2 and 3. We found Q4 and Q6. Next, let's try to find the reactions. So to find reactions, to find the reactions, the formula will be K into Q, which is K into Q minus F. So that is going to be the formula. That is R reaction equal to K into Q minus F. So you have to find it separately for element 1 as well as for element 2. So for element 1 you will have 1 and 2 nodes 1 and 2. At 1 and 2 you have q1 q2 q3 and q4, and q1 q2 q3 all are equal to 0. So q1 equals to q2, which is equal to q3, which is equal to 0. Therefore you are going to find that. So r1 r2 r3 and r4. So you're going to find all those. So let me just try to write the elemental stiffness matrix. So K1, so it's going to be 12, 30. So with this you got it at the beginning of the problem. 30, 100, minus 30, 50, minus 12, minus 30, 12, minus 30, 30, 50, minus 30 and 100. So this is all nothing but K. The values of Q, Q1, Q2, Q3 and Q4. Let's try to put Q1, Q2, Q3 and Q4. Q4 is 0. So this one, and that is Q4, and so we just got it in exponents. Once you try to convert it into, if you just try to divide it, you will get it in this form. And F1, F2, F3 and F4. So F1 is this, F2 is this, F3 minus 30 and F4 is 25. And 10 to the power of 3 will remain common. So here you have to do this K into Q minus F. So here you are going to multiply individually with everything. So this one, all this first row, second row, third row, when it multiplied with this first 3 elements, everything will go into 0. And here you have to find this. So that is very, very important. So what you're going to do, you are just going to, so you need to find the reactions of the supports. So reactions of the supports means it is, you have to find out all the 4 values, R1, R2, R3 and R4. So let's try to make it as easy as possible. So this first row multiplied with this column, okay, and then subtracting with this appropriate element in the matrix. So here, whenever you're trying to do 12 into 0 minus 30 into 0 minus 12 into 0, that's going to be 0. So 30 into this number minus of minus, so that you're just, when you're just going to add all that individually. Similarly, first 3 elements in this is going to be 0, because 30 into 0, 100 into 0, minus 30 into 0, that's also going to be 0. So only this, for this first 3 rows, only this last element you're going to consider and just going to substitute. And for R4 we are going to do it like this. So R4 alone I'll try to show you one. The other things are going to just be similar. So 30 into 0, again it's going to be the same, because this first 3 elements, wherever you are trying to do it, it's going to remain the same only. So you can ignore this first 3 elements, because when multiplied with 0, it's going to remain 0. Only this last column we are going to multiply with this 0 minus 6.03, something like that. So here I'm just going to show R3. So 30 into, and this 8 into 10 to the power of 3 is going to remain common. So minus 6.3, this one, minus minus into minus is going to be plus. So minus into minus, that is going to be plus 30 into 10 to the power of 3. So when I try to do it, I'm going to get the answer as R1, or answer of R1 as 21.429 Newton, because reaction is also a kind of force. So similarly, R2, I'm going to get it as 10.714 Newtons. R3, I'm going to get it minus 38.571 Newtons. And R4, I'm going to get it minus 53.571 Newtons. So that's what I'm going to get it, R1, R2, R3 and R4. Next they have asked, find the deflections at midspan. So to find the deflections at midspan, so at midspan means at the middle of the beam. So that is what is the formula. So that is what they have asked. So the formula is going to be like, so y equal to, I have to write the Hermite shape functions, n1, n2, n3, n4, n into q. So that's what is going to be the formula. So y is equal to, you are going to write that n1 in the form of Hermite shape functions, 2 minus 3 zeta plus zeta square divided by 4, comma le by 2, 1 minus zeta square plus zeta cube divided by 4, 2 plus 3 zeta minus zeta cube divided by 4, and here it's going to be le by 2, minus 1 minus zeta plus zeta square minus zeta cube divided by 4, and multiplied by q. So n is going to be multiplied with q. And here at midspan, you're going to take for in terms of natural coordinates, at midspan the value of zeta is going to be 0, and to the left the value of zeta is going to be -1, and towards the right when you're taking value of zeta is going to be +1. So accordingly this is a natural coordinate system. So whenever you're using natural coordinate systems, the value of zeta at the midspan is going to remain 0. So when you're going to substitute that 0 over here, finally you're going to get it. So at midspan, so you can just put at midspan, value of zeta is going to remain 0. So finally y equals to, so here it's going to be 0, 0, all that. So 2 by 4, only 2 by 4 you're going to get. That's nothing but going to be 0.5. And similarly here all this is going to be 0, 1 minus 0 minus 0 square plus 0 cube. It is just going to be 1 by 4. That is nothing but 0.125 into 1 by into it is nothing but L, and value of L. So L is going to be like 0. I mean, L is nothing but 5. So if we just try to substitute all this for element 1 and for element 2 separately. So for element 1, L value is going to remain 5, and for element 2, L value, element 2, let me try to write that, element 2, L value is going to remain 5 again. So here it's going to be like 0. So 1 by 4, 1 by 4 is 0.5. So it's going to be 1 by 4 into 0. Or into 5 by 2 into 5 by 2. L is 5 by 2. So similarly here it's going to be like whenever you're trying to substitute everything, it's going to be, so 2 by 4. 2 by 4 is 0.5 directly. And finally here you're going to get like 5 minus 5 by 2 into, so it's going to be plus 5 by 2, not minus 5 by 2, into minus 1 by 4. So upon solving all those, and q value is nothing but going to be q1, q2, q3 and q4. So for element 1, you're going to put the values of q1, q2, q3 and q4. So let me try to substitute it here. Finally, the value of y is equal to, so the value of y for element 1. So for element 1 you're doing, you have to do it separately, the value of, deflection at midspan for element 1 as well as for element 2. So the value of y, that is for element 1, is going to be 0.5, 0.125 into 5 and 0.5 minus 125 into 5. That is value of this one, and q1, q2, q3 and q4. So this is going to be like that, and upon solving that you will get all this. So you're going to get it like this. So the value of the deflection at midspan for element 1 is going to remain like this. This is for element 1. Similarly for element 2, you're going to consider 3, 4, 5 and 6. That is q3, q4, q5 and q6. So y at mid is going to be like 0.5. This is going to remain same. This is not going to same because they are nothing but standard Hermite shape functions. So this is nothing but going to remain same. So this is never going to change here. So this is completely going to remain same. So in this formula, if you are substituting zeta value as 0, 2 minus 0 plus 0, it's going to be 2 by 4. 2 by 4 is nothing but 1 by 0.5. And L value is going to remain 5 for element 1 as well as element 2. So for element 2, again 5 by 2 into 1 by 4. So it is going to be like 5 by 8. So 5 by 2 into 4 is 8, but 8. 5 by 8 is going to be like 0.125, something like that. So same here, you're going to enter Q3, Q4, Q5 and Q6. So it's going to be like this. So Q3, Q4, Q5 and Q6. So upon solving, you're going to do matrix multiplication over here. So upon solving, so y at midspan for element 2, it's going to be minus 27.9 mm. So this is how you're going to solve the problem. In this problem, we first solved, we just solved the displacements. We just found out the displacements Q4 and Q6. Then we just found out the, so first we all solved all this, like doing the FEA model, elemental stiffness matrix, global stiffness matrix, then using the load vectors, applying boundary conditions. We just got this Q4 and Q6. And finally, we just got this. We just found out the reactions R1, R2, R3 and R4. And finally, we are just doing this, deflection at midspan. So this is all about the problem. I hope you understood. Thank you.